So my projects are based on the theory of hybrid orbitals, and they explain a lot of things, but what I'm going to use them to explain is the geometry of certain molecules. They display the geometry of certain molecules from the most basic to the most advanced very well. There's something you can hold and see. It's better than just drawing it. It just gives students something to see and hold. So right here we have the most basic of the SP hybrid orbital, a linear molecule. Moving down, we have a trigonal planar, the SP2. Going down even further, we have a tetrahedral molecule, SP4, with 4 electron bonding sites. This is probably one of the most common molecules you will see, the common molecule types you will see in general chemistry. Moving further down, we have the beginning of the D orbital characteristic hybrid orbitals. We have the SP3D2, which is 5 bonding sites. This is where you get into more advanced molecules. And then here you have the octahedral, which has 6 binding sites. So again, like all this does is just really helps students have something to hold, something to see, to retain this information, because it's one of the harder things to do when you're just starting to get into the field of chemistry, especially as a high school student. This is one of the most fundamental things for drawing structures, and if you're going to take it to the next level, you need to have mastered this. And this is a great way to build a foundation for the retention of that information.
So what I did my first project here on is molecular geometry and basically the history of it. So molecular geometry is a way to describe how atoms bond to each other using geometrical shapes in 3 dimensions. So as you can see here, first I have this one here, straight line, it's linear, and this happens when you have the atom in the center bonded to 2 other atoms 180 degrees apart. This one here is trigonopyramidal, which happens when you have an atom in the center that would usually have 4 bonds, but the top is an unpaired, is unbonded valence electron pair. And here you have an atom that can usually form 5 bonds in the center, forming a trigonal bipyramidal shape. And basically what this is supposed to do is it's supposed to characterize these molecules physically. The first person to come up with this kind of modeling was John Dalton with his stick and ball model of the atom, and that eventually led to the molecular modeling kit that we use in CHEM329 lab. Hi, my name is Ryan Drake, and what I did my project be on for Yoko's class is electron tunneling. So basically, to give a little bit of background first, every electron is associated with a certain wave function. And what that wave function does is it characterizes the electron's position in space using X, Y, and Z coordinates, basically 3 dimensions. And for each wave function and the electron, it's also associated with an energy value in an equation called Schrodinger's equation. Now, in order for an electron to tunnel through a barrier, it has to overcome the potential energy of the barrier, which is typically higher than the energy associated with the electron. So in order to compensate for that, the electron absorbs the extra energy and becomes an excited electron, or is in an excited state, which is unfavorable to the electron. So the possibility of this happening is extremely low. So as you can see here, we have the 1-dimensional particle in the box, which is if you took one straight line of space from left to right and you tried to find the location of the electron in that space, this would represent the most probable location of the electron. And next to it is the V equals 1, 2, and 3 graphs for the electron tunneling through the barrier as shown on the side. And basically, the V equals 1, 2, and 3 is in reference to the energy difference between the potential energy barrier and the electron's energy and the wave function energy. And like I said before, this is extremely low possibility of happening, but Heisenberg's uncertainty principle, which states that you can't know for certain the exact position and exact momentum of the electron. Basically, that translates to there is always a possibility. The possibility is never zero of it happening.
Hi, my name is Chandler Madison, and for my Project A for Topics in PChem, I decided to represent the double slit experiment performed in 1802 by Thomas Young. And this experiment proved to be really influential to our current understanding of science, particularly chemistry and physics today. In 1802, Thomas Young was suspicious of the idea that light existed only as a particle. So he devised this experiment to demonstrate that when you pass light through two parallel slits, that it actually passes through both slits at the same time, interfering with itself on the other side. And these results were groundbreaking at the time and caused the entire science community to reconsider what they thought light existed really as. Hi everyone, my name is Chandler Madison, and for my Project B for Topics in PChem, I chose to represent the quantum harmonic oscillator. This model is extremely useful, particularly in chemistry, to represent electrons present in chemical bonds. The way that we model this in quantum mechanics is we consider the electron within chemical bonds to act like a spring, which leads to this sort of model. So what's significant about this model is at low energies, electrons act completely different than we would expect a spring to act in our classical world, where they're traveling really fast at the edges and slow in the middle, which is completely opposite to what we would expect. But as you go up in energy, the system starts to represent what we would expect from a classical spring system, traveling fast in the middle and slower at the turning points. So I found this incredibly significant when I first learned about it, and that there's a point where quantum mechanics, as you go up in energy, loses efficacy, and classical mechanics takes over.
Hi, I'm Rachel, and this is my Project A, where I talked about ice 9. So here you can see the regular structure of ice that you find in your everyday life. And you can see it's hexagonal in shape. But at different pressures and temperatures, you can see that the structure of ice can change very dramatically. This is called ice 9, and it's tetragonal in shape. And it's created at 150 degrees Kelvin and at a very high pressure of like 200 to 400 megapascals. So ice can exhibit a lot of different structural changes with its crystalline structure at different pressures and temperatures. So here, that's what I have that you can visually see and compare the two different structures. Hi, I'm Rachel, and for my Project B, I did particle in a ring at different energy levels. So at a quantum scale, a particle fixated on some radius r can exhibit a lot of different properties depending on its energy level. So for here at n equals 0, it's a complete cylinder. Basically, the particle can be found at any probability along this cylinder. At n equals 1 and 2, the probability of the particle changes dramatically, as you can see represented by these curves.
And you can see so here would be this is water. And basically it's all the shallow.
Thanks for coming.